Yes. Yeah, I'll talk about that in a second. All right, hello everybody. Welcome back. Hope you all had a good weekend. Some announcements. So in efforts to stay on track, make sure all of you are ready for Gen Chem 2. We're starting Chapter 8 today, and then there will be a recorded lecture for just to watch by next Monday. So it'll be less than an hour like our normal class time. It'll be posted hopefully Wednesday, but definitely, of course, over the break. So that will be required before we start class next Monday. Now, there will be an achieve, but I'm going to make it due on Tuesday instead of Monday. That way, when we're in class on Monday, we'll do a couple of practice problems that relate to content in the recorded lecture. And then plus I have an office hour that day, so if you have questions about any of the content, we'll be able to review it like in person on Monday. I'll make that achieve shorter as well, because I want you all to enjoy your break. Don't want you doing chemistry all weekend. I do have an office hour today at 1 p.m. and then for the exam, so I won't have them graded until next week. But I did have a student in my other section that was like on the border of whether or not they were going to drop. And so the drop date is today if you want to withdraw from a class. If you are in that boat where you're not sure, I can grade your exam today. I just don't have enough time to grade everybody's today. So if you're in that boat, just send me an email, let me know, and I can grade it later today and tell you what your score is. Just give you more information about how you're doing in the class. And this is not to scare anybody. Just if that was on your mind, then I can make sure you have your scores. But otherwise, they'll be ready to return next Monday, next time we meet. So no class Wednesday. This will be the last time we meet until next week. Questions about any of that? All right. We're going to jump right into Chapter 8. So Chapter 8 is all about quantum chemistry, the quantum model of the atom. And we're going to talk a lot about electrons. And if we think about an atom, it has protons, neutrons, and electrons. Protons and neutrons will tell us what atom we're working with and the mass of the atom. Electrons are kind of where the interesting part of chemistry comes up. So chemical reactions happen with transfer of electrons. And we're going to talk about neon signs today, like outside of a store that says open, that sign is energy that's released by electrons. So we're talking a lot about electrons, the energies of electrons, absorbing and releasing energy. All of that is in this chapter. So here are the sections. I'm not going to review them. Here are the learning objectives, as we always have at the beginning of the chapter. And our first section is just a brief exploration of light. So we're going to talk about some properties of light. On this slide here, we have the spectrum of electromagnetic radiation. So visible light, which is shown right here, visible spectrum, this is the small portion of this larger spectrum that we can perceive with our eyes. So all the different colors, different energies of light, wavelengths of light, are within this small part of the electromagnetic spectrum. Higher energy, so to the right on the spectrum is higher energy. We have ultraviolet light, X-rays, gamma rays. And then lower energy, we have infrared, we have microwaves, radio waves, and longer radio waves. So the electromagnetic radiation spectrum, electromagnetic radiation in general is helpful for studying atomic structure. And as I just said, light is one type of electromagnetic radiation. And what distinguishes different types is the energy of that radiation. Now, light has wave-like properties, so we can describe energy of light using these properties that we can describe waves. So a wave is a regular oscillation in some particular property. Waves can be described by frequency. So this is the number of wave crests passing a point in space in one section. A wave crest, so these graphs on the right side represent 3 different waves. They all have different wavelengths, which we'll get to. But a crest is that top of the wave. So here's a crest. So frequency is the number of wave crests passing a point in space in 1 second. The symbol is the Greek letter nu, which looks a lot like a V, but is a little bit different. So that is the symbol for frequency. We'll see that in equations. And since this is the number of wave crests passing a point per second, the units are per second. So second to the negative first power, or hertz, which is the same thing as second to the negative first power. 1 hertz is 1 second to the negative first power. Next, we can describe wavelength. So wavelength is the distance between successive wave crests. So it's represented in each of these graphs here. So here we have a pretty short, relatively short wavelength, a little bit longer in this middle graph, and even longer in that top graph. The symbol for wavelength is lambda. That's a Greek letter for the letter L. And we're talking about a length. So for low energy waves, they have longer wavelengths, and this would be often meters is what's used. Higher energy, shorter wavelengths can get really, really small, so we might use nanometers. When we're working in the equations, whatever we have, we will convert to meters. And then last we have amplitude. And this is the height of a wave. So from the center to the crest would be amplitude. I have a little bit more about amplitude on the next slide. So 2 different graphs here. One has a higher amplitude, one has a lower amplitude. And if these are light waves, then if we have a higher amplitude, we'll have a brighter light. If we have a lower amplitude, we have a dimmer light. You can see the wavelength is about the same in both of these, but the change in amplitude impacts the brightness. Okay, so if you have a light bulb and you turn it on, light is sourced from that light bulb and it will travel to fill the room. And so light, we say, has some speed, the speed at which it would travel from the source to some identified endpoint. Having gaseous molecules, other things in the atmosphere, different particles in the atmosphere can affect that speed. But in science, we define the speed of light as how fast light is traveling in a vacuum. So no gas molecules, no particles, there's nothing blocking the light traveling. It travels at a speed of 2.99792,458 times 10 to the 8 meters per second. So distance in meters and second for time. So that is the speed of light. And we use that for all of our calculations. So even though when we're talking about light traveling on Earth, it's not in a vacuum, it's still approximately the same value. The speed of light is lowercase c. So if you see lowercase c, that is our speed of light. This value is provided to you on that periodic table sheet, so you don't need to memorize it. But also, we'll use a rounded value. So we'll use 3.00 times 10 to the 8th meters per second. That's sufficient for our class. On your periodic table sheet, it says 2.998 meters per second. If you're doing a calculation, you can use that value. You can use 3.00. It's going to be a really small difference. And so either way, that's not going to be the difference between a correct and incorrect answer. So yes, this is our speed of light. And the speed of light is equal to the wavelength, so lambda, units of meters, times the frequency, nu, which is in units of seconds to the negative first power. So we have meters per second as our speed of light. And we can use this equation in the speed of light. We have this as a constant. This is never changing. So if you know one of these, you can find the other. And that's what we'll do on the next slide. So here we have an FM radio station transmitting its signal at 88.1 megahertz. And we're looking for the wavelength of the radio signal. So we're provided a value, 88.1 megahertz. What does that tell us about what property does that give us information about of this wave? Yeah, it's the frequency. So hertz is a unit for frequency. So we know the frequency. We're looking for wavelength. I'll have you all start. You'll use this equation here. And if we go back to our electromagnetic radiation spectrum, radio waves are in this region here, where our wavelength is between 10 to the negative first power, so 1, and 1,000 meters. So your unit here. Okay, I'll give you all a minute or two to get started and we'll go through it together. Okay, we'll go through this together now. So we will use speed of light, c, is equal to wavelength lambda times frequency, nu. Remember, c, speed of light, is 3.00 times 10 to the 8th meters per second. Lambda, wavelength we're looking for, and I have frequency at the top. So if we're using the speed of light in units of meter per second, then our frequency better be in units of per second, and we'll get a lambda value in units of meters. Our current frequency value is in megahertz. Remember, 1 hertz is equal to 1 second to the negative first power. So we'll need to convert megahertz to hertz. And this prefix mega, you might remember, I think it was from chapter 1 when we learned about all the prefixes. 1 kilometer is 10 to the 3rd meters. The next highest or higher prefix that we use is mega, and that's 10 to the 6th. So 10 to the 3rd is kilo, 10 to the 6th is mega. So 1 megahertz is 10 to the 6th hertz. And we want to cancel out megahertz. So 1 megahertz in the denominator, 10 to the 6th hertz in the numerator. So this is 8.81 times 10 to the 7th hertz. And remember, this is also seconds to the negative first power. All right, so we have speed of light equals wavelength times frequency. If we're just looking to find wavelength, we can do speed of light divided by frequency is equal to wavelength. So we have 3.00 times 10 to the 8th meters per second divided by 8.81 times 10 to the 7th seconds to the negative first power. Now, reminder here, if you have, for example, meters per second, this is equivalent to meters times second to the negative first power. That's what that -1 indicates, is that. So we're canceling out per second, second to the negative first power. We have units of meters, and that's good because we're looking for wavelength. We need a unit of length, and this is 3.41 meters. So really, any frequency, any wavelength of light, as long as you know one of those two, you'll be able to calculate the other. This specific example was about radio waves, and look, the wavelength is 3.41 meters. That's 10 or 11-ish feet. It's a very long wavelength. Questions on this? Okay. Well, talk a little bit more about light and electrons. So this photoelectric effect is observed for a surface of a metal. What happens is electrons are ejected from a metal surface. So this is showing a metal surface here. This is showing light shining onto the metal surface. If this light is of sufficient energy, it will cause electrons to be ejected from that metal surface. So this is how a lot of light sensing devices are generated. They use this property. So light results in the ejection of electrons. This shows us, or this tells us that electrons can absorb energy. They can absorb energy from light and be ejected. So the number of ejected electrons can be measured with electronic devices, can produce a readout on a computer. So this next slide shows a schematic of that. So we have a metal surface hit with a beam of light. Electrons are ejected from the metal surface and reach the detector, and you can get information about the number of electrons, energy of electrons that are released from that metal surface. The energy of the electron released is related to the energy of the light that the metal surface is exposed to. So we're going to talk a little bit more about this light. And so light comes, we can describe it as coming in packets or bundles, an amount of light, and we call that a photon. So a photon has energy that's directly proportional to its frequency. So light has, we said light has properties of waves. We can define its frequency. The energy of the photon is proportional to the frequency of that light, the wavelength, or the frequency of that light. Yeah. So energy of a photon is equal to the frequency of that photon times this constant here, h. This is another constant that's provided for you on the periodic table sheet. This is Planck's constant. So h, Planck's constant, never changes. It's constant. It's definition of a constant. So if you know the frequency of light that is absorbed by that metal surface that's hitting the metal surface, then you can calculate the energy of the photon that is reaching that metal surface. So we'll do that on this next slide. We are calculating the energy of a photon of blue laser light that has a wavelength of 488 nanometers. So we're given lambda wavelength. It's in units of nanometers. We'll need to convert that to meters to finish the equation. And then we'll need to use two equations. So we have on the previous slide, energy is equal to Planck's constant times frequency. But we don't have frequency. We have wavelength. So we need our other equation that the speed of light is equal to wavelength times frequency to then find the energy. So if we rearrange that second equation to solve for frequency, we have frequency is equal to speed of light divided by lambda. Now we can combine these two into energy is equal to Planck's constant times the speed of light divided by lambda. Okay, I'll give you all a minute or two to continue working. So we're looking for energy of a photon. If you finish that second question, it's energy of 1 mole of photons. Okay, so we'll use E equals hc over lambda. H and C are both constants, so we don't need to calculate them, they're provided. And then lambda was provided in the question statement. Now, Planck's constant is in units of joules times seconds. Speed of light is in units of meters per second. Our wavelength currently is in units of nanometers. So we need to convert nanometers to meters before we can plug it into the equation. So 488 nanometers, and we use our conversion 10 to the negative 9th meters is in 1 nanometer. So this is 4.88 times 10 to the negative 7th meters. And that's what we will use in the equation. Just for space, I'm going to move down here now. So E is equal to value for H, 6.626 times 10 to the negative 34th power, units of joules times seconds. C, speed of light, 3.00 times 10 to the 8th meters per second. And then our wavelength, we just calculated in units of meters, 4.88 times 10 to the negative 7th meters. I believe this equation here is also provided. You'll use this in a few different questions. I think that's on your periodic table as well. Okay, so if we simplify this fraction here, we get 245,298. And then let's look at our units. We have joules times seconds, and then meters times second to the negative first power. So seconds cancels out. And then we have meters in the numerator, meters in the denominator. These also cancel out. So we're left with units of joules. And that makes sense. We're calculating energy. Yep. You all got different answers? No one in my 9 a.m. checked my math. What's your answer? Oh, yeah. This is the answer for the second part. Sorry about that. You're right. It is 4.07 times 10 to the negative 19 joules. I forgot I needed space for the second question. Okay, so this is the energy of one photon. If we want to find the energy for a mole of photons, how can we do that conversion? We would multiply by Avogadro's number, but you have the right idea.
But what if, like, when you convert, like, the moles to be on top and then the conversion to the bottom?
Good question. So this is joules per photon, and we want it to be in joules per mole. So mole will be in the denominator. So I'm going to do this in a different color to help separate. So part 2, we have energy of one photon as 4.07 times 10. I'm not going to have enough room there. I'm going to erase what's on the top and work up here. All right, 4.07 times 10 to the negative 19 joules, and this is per 1 photon. So if we want it per 1 mole of photon, well, 1 mole of photons is equal to 6.022 times 10 to the 23rd photons. So we use that number here, 6.022 times 10 to the 23rd photons is equal to 1 mole of photons. So we cancel out unit of photon and we're left with joules per mole of photons. So that's why we multiply by that number. And this is 245,298 joules per mole. Okay, questions on this? All right. Well, go to 8.2. We're getting more and more exciting information. So 8.2 is all about the Bohr model of the atom. We'll talk about how electrons can absorb and release energy. This could be visible light. So we have to talk about energy states of electrons. By convention, scientists define a free electron that's at rest. So it's not moving, it's not bound to an atom, it's a free electron that has an energy of 0. So then if we have an electron that is in motion, now I'm looking at the very top here. So here's free electron at rest. Free electron in motion is now a higher energy electron. So this has positive energy. Relative to this defined 0 point. So it has more energy than if it were a free electron at rest. Then electrons that are bound to a nucleus, so orbiting a nucleus, they have lower energy. So they have negative energy values. They have lower energy than a free electron at rest. So an electron that is part of an atom in orbit of a nucleus has lower energy than if it were not part of an atom, if it were at rest. So this means that if an electron binds or becomes it's now orbiting in a nucleus, it's losing energy. So energy would be released if it started at rest, or it started as a free electron and then is now orbiting a nucleus. And the more tightly bound the electron, the lower its energy. So we'll use this to explain, we'll talk a lot about absorption and emission. So this image here shows the positive charge is representing the nucleus. We have protons in the nucleus. And then these N numbers are showing different energy levels that an electron could exist at. Lower number means closer to the nucleus. So if an atom absorbs energy, an electron would gain energy and it would travel further away from the nucleus. So it would end up at a higher energy state. If it starts at level 1, it could go to level 2, it could go to level 3, it could go to level 4. Depends on how much energy and what wavelength of energy is provided to the atom. But that requires energy for an electron to go from closer to the nucleus to further away from the nucleus. So atoms absorb energy when electrons are raised to a higher energy level. So that increasing in energy level is a result of absorbing energy. Once the electron is at a higher energy level, it could relax back down to a lower energy. So that's what these blue arrows are showing on the right. The electron starting at a higher energy and can relax back down to a lower energy level closer to the nucleus. Remember, closer to the nucleus is lower in energy. And when that occurs, atoms emit energy. Oops. So if electron falls from higher energy to lower energy, that means the electron is losing energy, and that can be emitted in the form of visible light. The next slide just has some vocab that we use to describe energy levels of electrons. So if an electron is in its lowest possible energy state, we say that it's in the ground state. So that would be at n equals 1 in this diagram. So the ground state is the lowest energy state of the atom. All of the electrons are in their lowest energy states. This is the most stable state. And then in an excited state, this is when in an atom that was in its ground state has absorbed energy. So now its electron is at a higher energy level. Once an atom is in an excited state, it can then give away energy by the electron dropping back down to its ground state. So different elements have electrons, can have electrons in different positions. They have a different amount of protons in the nucleus. So it requires different energy for electrons in atoms of different elements to jump energy levels or to relax energy levels. So an absorption spectrum will be different for different atoms. So each element has its own unique absorption spectrum. Well, let's look at this picture here. So we have a gas-filled tube here. There's some gaseous element in this tube. We have a lamp shining light through a slit into the glass tube, and then some of the wavelengths of light or frequencies of light is absorbed by the gas atoms. That's causing the electrons to jump in energy state. Whatever is not absorbed is transmitted through that glass-filled tube, and then if we use a prism to show the different wavelengths of light, then we can see from a detection screen which wavelengths of light were absorbed by that gas. And this will be different for different gaseous elements. So as light passes through the tube that's filled with the gas will absorb light at specific wavelengths. And so transmitted light is low at those wavelengths. So the wavelengths that are absorbed by the gas absorb some of that energy, and so that's what's shown by these darker lines on the picture. It might be easier to see on your slide. The atoms in the gas have absorbed some of that wavelength of energy. So this is the absorption spectrum. We can also look at an emission spectrum. This is also unique for different elements. We all quiet down? So each element has its own unique emission spectrum. As a current is passed through a tube filled with a gas, so we have a tube filled with gas, we have a current passing through this tube. The electrons have gotten excited from the current, the energy that they're absorbing, and then they relax back down and they release energy. So as they release energy, that's producing some light around the glass tube. So this is how neon signs work. Energy is provided to neon gas or different gases. They will emit different wavelengths of light, and that is visible light for certain gases. So if we shine that light through a slit and then through a prism, specific wavelengths of light, which can show up as different colors, are emitted by different atoms. And so let's see. They emit light at specific wavelengths. We use the prism to separate the wavelengths, and we can see which wavelengths of light are emitted by a specific gas in the tube. Different elements emit different wavelengths of light. They have their own emission spectrum. So each frequency absorbed or emitted by an atom corresponds to a particular energy change for the atom. And these characteristic patterns of any energy gains and losses provide information about atomic structure. So the structure of the atom. So sodium, if you shine light at sodium gas, if you put sodium gas into a discharge tube, it will emit wavelengths of light only in these two ranges here. So the two yellow lines. Mercury emits red, orange, yellow, green, blue, a little bit of purple. Neon, red, orange, yellow, and a little bit of green. So this will always be the same. This is what the emission spectrum looks like for all neon atoms. And what's happening is the electrons are absorbing energy, then releasing They go back down to ground state. As they do that, they emit energy. The energy levels that an electron can fall to emit energy is different for different atoms. And so that's why we see different emission spectra for different elements. So we'll talk a little bit more about that now. So electrons bound to atoms only have certain energy values. And in other words, we can say that atomic energies are quantized. So this means that absorption and emission can only occur at certain frequencies. If we go back to the slide, we look at sodium. It emits light at this frequency and this frequency, but nothing in between, nothing larger or smaller. That's because there are very specific energy levels that an electron can excite to and thus fall from. So this is a general energy diagram here, just to show that if we have a ground state electron, it absorbs energy from a photon. In this general example, this electron could excite up 1, 2, 3, 4 energy levels. Then it could fall back down certain energy levels, and the difference in those energy levels correspond to the energy of light that is emitted. So all of the energy that's lost or emitted from the electron falling back down to a lower energy state that's equal to the energy of the photon that's emitted when that electron relaxes back down. So these are very complicated when we get into atoms that are larger than hydrogen. So we'll talk about values for the electron absorption and emission for hydrogen atoms because it's the simplest atom. We won't do any other atoms because they're complicated. If we just go back to this slide, we would have different values for the energy emitted at every single line that's shown here. Again, hydrogen's a little bit simpler. So most elements have complex emission spectra, but the emission spectrum of hydrogen is simple enough for us to calculate. So we have an equation here for the frequency of the energy that's emitted from the hydrogen electron relaxing from one state to another lower energy state. We have a value here, seconds to the negative first power, so frequency units. And then 1 over n1 squared minus 1 over n2 squared. n1 and n2 are integers, so there will only ever be whole number values, 1, 2, 3, 4, etc. These are the energy states that the electron starts at, that's n1. The energy state that the electron ends at is n2. So since energy states can only be 1, 2, 3, 4, etc., light can only be emitted at certain frequencies, at values where n is equal to those integers. So the energy, think about electron, let's say it's absorbing energy, starts at a ground state at level 1 and it excites to level 5. Then the energy that's absorbed is equal to 2.18 times 10 to the negative 18 joules, this value here, times 1 over its initial energy state, so we said that was level 1, minus 1 over its final energy state, I think I said 5, I don't remember, but that's what this equation is telling us. So this will tell us how much energy is absorbed by an electron or by an atom if it excites, if an electron excites to a higher energy state. It can also tell us how much energy is released by an atom if an electron relaxes back down to ground state. And both of those really tell us the energy change of that overall atom. This next slide summarizes all of that. So the change in energy of the atom is the difference between the two energy levels of the electron. So when absorption occurs, an atom gains energy. The electron is gaining energy. The electron is part of the atom, so the atom gains energy. So delta E for the atom is positive. The amount of energy absorbed by the atom, so the change in energy of the atom, is equal to the amount of energy of the photon that the atom absorbs. So all of the energy from the photon is transferred to the atom. So that's when an atom or an electron absorbs energy, goes to a higher energy state. If an electron is already at a higher energy state and relaxes back down, the atom loses energy. And so delta E for the atom is negative. It has lost energy, so change in energy is negative. The amount of energy that the atom lost is equal to the energy of the photon that's released by that energy, that change in state of the electron. So an electron at a higher energy state relaxes back down. It's losing energy in the form of a photon. The energy of that photon is equal to the energy change of the atom. So the energy of a photon must be positive. And whatever energy is lost or gained by the atom is equal to the energy of the photon absorbed or released. But because this must be positive, we say the energy of the photon is equal to the absolute value of the change in energy of the atom. Questions so far?
Can you explain again why it has to be positive?
Yes. So we are not, so when we're talking about the energy of a photon, that's just the amount of energy that is held by the photon. Photon has some energy. So that can't be negative for something to have negative energy. We can say the change in energy is negative, but if something has energy, it's positive. So if an atom absorbs energy, delta E is positive. It's absorbing the amount of energy that the photon provided. If the atom is losing energy, it's losing the exact amount of energy that the photon released will have. So that is always positive. Okay, we have this question here. We are looking at the energy change when an electron in a hydrogen atom changes from the fourth energy state to the second energy state. So we're looking for energy change, and then what's the wavelength of the photon emitted? So first we need to find change in energy of the atom. An electron in hydrogen changes from the fourth energy state to the second energy state. So we will use that equation from 2 slides back. Energy, or change in energy of the atom, is equal to 2.18 times 10 to the negative 18 joules times 1 over n1 squared. By the way, this is provided for you on your sheet as well. Minus 1 over n2 squared. Don't say it out loud, but think to yourself and tell the person next to you, what is n1, what is n2? Okay, N1 is our initial energy state. So what's our initial energy 4. Yeah, we start at level 4 and then we go to level 2. So N1 equals 4, N2 equals 2. These will always be integers. So that means for our equation, we have 2.18 times 10 to the negative 18 joules divided by N1 squared, so 4 squared, minus N2 squared, so 2 squared there. Then if we solve this equation, we have negative 4.088 times 10 to the negative 19 joules. Now we think, does it make sense that this value is negative? Well, we're starting at energy level 4. Electron goes down to energy level 2, so the electron is losing energy. It's releasing energy in the form of a photon, and the atom overall is losing this amount of energy. Okay, we will end there. I will do the second part in the video, and we'll continue with the notes there. Thanks, everybody, and I hope you have a great break. Thanks. Thank you.